Hello there, my name is Zachary Kottman, and I am going to walk you through problem 6.8 in our 3260 System Dynamics and Vibrations homework. Alright, so I've drawn the circuit that was given, and we have to obtain a model for the voltage output of the circuit across these 2 points. V out, and then find V out if the input voltage is a magnitude times a unit step. So I've drawn the circuit, and I wanted to make a few comments on the given solution, and maybe show where it might be a little better to do it a little differently, and then I'm also gonna hopefully compare the way that I do it here to using the impedance method. Okay, cool, let's get started. So the first thing I wanted to kind of point out here was that in the solution given, these points here, here, here are all labeled as 0 volts, and then this point is labeled as V out. We've got VS here, which corresponds to this VS, and then when we're talking about the sum of the currents into and out of this spot right here, we have I3 equals C ddt V naught minus 0. And the fact is that these being 0 and this being the case, this is not always true, and so you really shouldn't, like, there's no ground attached here. You can't assume that this bottom is 0, and you shouldn't assume that. You don't need to assume that. And if you can't assume that this bottom part is 0, you also can't assume that this is V out, because V out is the difference between these 2 points, and this is V out only if this is 0, and you can't assume that. This voltage signal could be an AC signal, which means that at some point in time this voltage here is going to have a positive magnitude, absolutely. And so and that would not be, it would not equal 0. It's just not a very good practice to assume that something that is not grounded equals 0. So instead of calling this 0 and that V out, I'm just going to call, and actually just for notation's sake, I'm going to say we have V1 here, V2 here, and V3 here. Now, and we'll get to it in a minute, but I'm kind of jumping the gun with this current thing. What that means is that this I3 will be V2 minus V3. Now, it's always absolutely the case that V2 minus V3 equals V out, so that I3 then becomes the capacitance times the time derivative of V out. But it's not always the case that V2 does not always equal 0, or sorry, that would be V2 does not always equal V out, and V3 does not always equal 0. It depends on your voltage source here. There's no ground. So, and you don't need to assume this. You don't need to assume that this is 0 to solve the problem. It's so it's actually just something you shouldn't do. Okay. So we'll get started on solving the problem. And to the point where that I'm making here, where this this equation here, V2 minus V3 equals V naught. This is kind of how I see all the sections of the circuit. If I was just to label this and kind of go about it in my own way, I wouldn't label the voltage here and the voltage here as V1 and V2. I would just say that there's a voltage change across this resistor, and I would call that V1. And there's a voltage change across these points called V out. So as you go from this point to this point, there's a voltage change V1. As you go from this point to this point, voltage change V out. And then the sign of that voltage change depends on which direction you choose the current to go. So if we say the current's going this way, and the current goes from here this way across this resistor, we know that the voltage will drop across that resistor in that direction. So we actually have a voltage drop across R1. And then, since we're saying too, the voltage goes down through this, or the current goes this way, current goes this way, we know that we're going to have a higher voltage here and a lower voltage here, so we have a voltage drop across this. And so then we can do Kirchhoff's voltage law, and we just have Vs. And this is a positive Vs. If you think you follow the current, when you go across a battery, you go, or some voltage source, you go from negative to positive, you're going up in voltage. So we have a plus Vs, and then we go across a resistor, so we're going to go down in voltage, minus V1. We go across these elements, we're going to go, if the current goes this way, we're going to go down in voltage, minus V out, and then we're back over to this back part of the loop, so we've gone all throughout the loop, and so that's equal to 0 by Kirchhoff's law, voltage law. We could have said that the current goes this way, which would kind of be silly because we have a plus here and a minus here on our voltage source, but all that would do is flip every single sign here. We would get minus Vs plus V1 plus V naught equals 0, and obviously these are the same equations. So as long as you stay true to which direction you pick the current to go in, you can get the signs correct. Anyways, yep, cool. So let's see. The next thing we are going to use to solve this problem is the current going in and out of this node. We have I1 coming in, and then I3 and I2 going out. So minus I3 minus I2 equals 0. So obviously we have I1 equals I2 plus I3. And I like to use capital I just because sometimes I use lowercase I for imaginary numbers instead of J, and even if I'm using J, little J and a little I, they look all the same to me, and I don't like that. Anyways, so, and then we will then take our relations between current and voltage and plug them into here using this equation and this equation, and we'll come up with the form of the differential equation for V out. So the current I1, the current here, I1 is going to be equal to the voltage drop across R1. So it's going to be divided by this resistance R1. So I1 equals V1 over R1. And from this equation we have that V1 equals Vs minus V out. So Vs minus V out over R1. So that's I1. I2. I2 equals the voltage drop across here divided by R2, which we just called the voltage drop across here V out. We're measuring the difference in voltage between these two. And then I3, and this you just go to your equations for capacitance and voltage, and you'll see I3, the current across this capacitor, equals the capacitance of the capacitor times the first time derivative of the voltage drop across the capacitor. And like I said, we're calling that voltage drop, that voltage drop is V out. Alright, so then we do get the equation that is given in the solution. That we then solve for V out. So in the solution, it did work out to call this 0 and call that V out, but that would definitely be confusing if you had an AC voltage source and you knew that sometimes this side was a positive voltage and not 0. And you don't have to call it 0. You can just call it, this V2 and this V3, and say that V out is V2 minus 3,3. This is always true, and you don't need to specify this as 0. If it was attached to a ground, if you had a ground here, absolutely this bar, all this stuff attached to the ground would be 0. But that is not the case. So, anyways, so we come to the differential equation that we were going to solve, and I'm going to make myself some space and rewrite that. All right, so I had some notes here on how I wanted to do this exactly, but I don't know what they are, so I'm just going to kind of wing it. So I lost that sheet. Anyways, so I don't want that stuff in the denominator right now, so I'm just going to work on rearranging this equation, just kind of see where I get. So multiply everything by R1, R2, R2 Vs minus R2 V out equals R1 out plus R1 R2 C V out dot. And then put all the V outs on the same side. So we're going to have R1 R2 C V out dot plus R1 plus R2 times V out equals R2 Vs. Awesome. Okay, so and then if we do this is just a straightforward, it's a first order ODE. You just do a Laplace transform really quickly, and this is pretty straightforward. No big deal. We're gonna get Vs V out S times S R1 R2 C plus R1 plus R2 equals R2 VS S. Okay, so this was the model in that was part A. We obtained the model. There we go. I mean, you can rearrange that model to look like this, or some other rearrangement, like we have in the solution in Homework 9 Solutions. But this is it, and all that we do is rearrange it to some other form that we want it to be in, and that can be whatever you feel is easiest for you to work with. In any case, I moved on to part B, and we're going to find V out as a function of t if V in is some magnitude times a unit step. So I'm just doing the Laplace transform, no big deal. So what we have here is, so I got to this equation, and I'm going to move over to my big white space here. So and then Vs of S equals the Laplace transform of V US T equals V over S. Okay, so then I'll have V out S equals, moving that over here, and I'm going to put SC plus R1 plus R2. This is R2. And then we're multiplying that by V over S. And actually here you can see this is the transfer function right there. Awesome. And then and this is the part that I definitely did not fully do this when I solved it earlier, because it's pretty straightforward, but the algebra can be a little annoying, so bear with me if I make a mistake, because we want S by itself here. So we're doing dividing that by CR1 R2 and then multiplying that by V over S still. All right. And from this form, and I'll put this in even more clearly. I'll write it one more time. These will cancel. This form is obviously something we know how to take the inverse Laplace transform of, or that we can. I think I need this to be equal to that, annoyingly so. So if I multiply the whole thing by that over that, equals and then this thing gets multiplied. Those cancel. R2 on top. So this term equals VR2 over. Hopefully I don't make a silly algebra error. Okay, oh boy, finally. So we have some magnitude we are multiplying everything by. That's just along for the ride. And then this transforms to 1 minus e to the negative times t. And take a look at the solution here. Okay, so somewhere along the way I ended up with a VR2 here instead of VR1. So I made some error with my R1s and R2s getting to this. But oh, that's frustrating. Oh, algebra, how I hate thee. This is why I should have fully solved it before doing a video. That's all good. R2 over that stuff. That is good. We divided through by CR1, R2, CR1, R2. So I'm going to cancel the R2 on top. VRS, and then we have an R1 on the bottom, and CR1, that's good. If I multiply the top and bottom by this guy, I get V times R1 plus R2 over which is A, which I need to keep with the, okay, so I'm just doing CR1 times CR R1 plus R2 CR1 R2. R1's cancel, the 2 goes to the top. C's cancel, R1 plus R2. This one over. Oh yeah, this was where you multiply. Okay, so Actually, there is a question here as to whether or not this should be VR2 or VR1. The solution for the homework has a R1 there. But you know what? In about 5 seconds, I can determine that actually should be R2 on top. Yep, R2. That should be V times R2 over R1 plus R2. That should not be R1, which is in the solution for the homework. And actually, if you look at the graph, it has R2 in the graph for the homework, and it's just rewritten a little incorrectly down in black as V naught, and this equals R1 times V. Okay, so R2 is the correct answer. That's what we expect. And a quick check is to look at like this thing just becomes a 1 minus e to the negative a t, which as t goes to infinity, this term goes to 1, and which means that v naught of infinity, or t going to infinity, I guess I'll write that, should equal VR2 over R1 plus R2. And we can actually just know that just from looking at this picture here. As time goes to infinity, this capacitor fills up with charge, and no current flows through it whatsoever once it fills up with charge. So then we just have two resistors in series, and the voltage drop across one of those resistors in series, R1, R2, is just going to be like VS. Part of VS is going to drop across R1, and part of VS is going to drop across R2. We'll still have, and I'll call this V1 and V2. Well, I'll call this V out, because that's the one we're measuring. Minus V1 minus V out equals 0. And just from some experience with this, and if you think about it a little bit, you're basically splitting the voltage across these resistors, and the amount of voltage you're going to see here is basically the ratio of that resistor to the total resistance times the input voltage. And so if Vs equals V times the unit step function, we just get VR2 over R1 plus R2 equals V naught. And that's for t going to infinity. It's a circuit without a capacitor. And so this is definitely the right answer. I didn't make any algebra errors. It was just a copy error on the solution on the homework. But in blue on the graph in the homework solution, you'll see that it's R2 in the numerator there. Real quick, I just want to show, and this is probably obvious to you already, but the transfer function, which equaled R2 over C R1 R2 SC R1 plus R1 plus R2. That's the same thing. Like, you're going to get this answer doing the impedance method, and I'm just going to run through the impedance method really quickly. So I'm going to draw a slightly new diagram, or draw the diagram again, just so I can put some different labels on it. Oh, that's the capacitor. So here, I'm going to call this Z1. I'm going to call C Z2. R2 is Z3. And then this together is